am Puneeth. I'm a PhD student with my husband at the University of Toronto. And I'll be talking about something called as Brownian bridges, which showed up in a couple of projects that I was working on. And so I'll start by talking about Brownian bridges and talk about two projects where it showed up for very different reasons. So neither of the projects, the focus wasn't Brownian bridges for any of it, but it just ended up being a tool that was very useful. So I thought it might be worth sort of chatting about it. That's not really combination landscapes, that's Meta with whom this work was done. And so he's here and he had a discussion on this topic as well earlier. So okay, so let's start with the basis of it, as the name suggests, is Brownian motion. So just as a recap, it's an object we have all encountered at least at some point in our eco-evolutionary lives. And you start basically at some location, you move with these normal increments that are nice because they're independent and these are stationary. So what that means just quickly is that if you take two intervals of the same length, the amount you move are identically distributed and they're independent of each other as long as they don't overlap. Most often, and this is not the only reason, but quite often it's invoked to model drift in these evolutionary questions, and particularly used in inference because if you have a tree, so say it's a phylogenetic tree between species, you can model the mean trait evolution along this phylogeny as a Brownian motion. And what it means to be these properties of independence means that these edges are all independent of each other, and all you need is the covariance amongst the dips, and that's proportional to the shared time of those species. So that kind of lends itself nice for inference, where you can infer ancestral states and evolutionary rates. Similarly, if that's a coalescent tree and spatial locations of the you can use sort of similar methods to infer dispersal rate and location of genetic ancestors along the tree. Okay, but sometimes there are restrictions on your trait or your model that make Brownian motion not the best, not ideal in its raw form. And the part where we encountered it, one was when we were trying to model Brownian motion down a network. And so you had these loops that showed up, and that the Brownian motion is no longer independent. So you see that these the root from 5 to 3 has to be equal to the root from 5 to 4 to 3. And so those two edges cannot be independent of each other. The other part where we were trying to model was a probability distribution instead of like a new single sort of trait, was a distribution. And that distribution has this property that you need to integrate onto one. So you can't sort of independently have Brownian motion at each of the locations, and there's some restrictions because of that shows up. And in both the cases, it turned out that the Brownian bridge was the object that we allowed us to make progress in addressing the problem. So what is a Brownian bridge? It's basically the Brownian motion, but conditioned on the endpoint being back to 0. So it can go wherever it wants, but towards the end has to come back to 0. And this is called as a Brownian bridge. It loses this nice property of these independent increments because clearly move towards the positive values early on, move down to get back to it. So you have this negative covariance that shows up. But it still has this nice property that if I take these two increments, they're not independent, so there's some covariance, negative covariance. But if I shift these two intervals by some value, that covariance still remains the same. So the covariance is shifted, and that's kind of nice and lends itself to some nice properties. Particularly, sort of just to emphasize that more, I've written this in some abstract form of like BT condition on being at time 1 being back at location 0. But that's a more sort of explicit formulation of that. You can write it down in terms of these Brownian motion. We know what the variance covariance of a Brownian motion is, and that allows us to compute the variance covariance of W of the Brownian bridge. That's W at different time points. And so that's what it looks like. So you can see that the covariance, the first term is the same as what you would see in a Brownian motion, and then there's some reduction because of this restriction of coming back towards the end. Generalizing this a little bit more, the time doesn't need to be 1, it can be any arbitrary time capital T, and the location doesn't need to be 0, it can be any arbitrary location X. Okay. So the first problem was, here's a bit more motivation of what the problem was. So we had this object, the ancestral recombination graph. So instead of a population, instead of a coalescent tree, and looking at a population where you have recombination, the object is a network. So you have this individual one, the genome of it sort of going back through individuals that are ancestral to it. And at one point, the genome splits because of recombination and goes into two different ancestors. And that creates this loop-like object that you want to do. The same thing recently, that over the last few years, there have been really good methods coming up to infer these arcs. And so suppose we have this arc, and we have the spatial location of the tips, so contemporary individuals can we infer sort of into the ancestors and sort of the dispersal rate of that ancestors that led to these present day distributions. So that was the question we were trying to model. And the problem was this loop again. So in order to compute the covariance between 1 and 2, we had some idea of what the covariance was between these 3 and 4 nodes, and that loop made it a little problematic to compute that. And so one of the earliest suggestions in this project was to sort of make a cut at 5. So at this point at the top, and because this Brown motion has some nice reversible type of properties, you end up with this object. So you can start from 5, go to 3, go to 4, back to 5. And so you start at 5, you end at 5. And that is the Brownian bridge. So you start at some location, you end back at that location, and you can fluctuate in between. And then you know what the variance covariance of a Brownian bridge is. You can compute the variance at 3, at 4, the covariance between them, and then you can do all the similar computations as you do in sort of the standard Brownian motion case. However, real life looks a little bit more complicated. So that's an arc for just 11 genomes in Drosophila. And you can see that the issue are loops that look like this. So two loops that are either in each other or stacked on top of each other, which means it's not sure where to cut it. You can cut it here first and then here, or you can cut it here first and then back on the stop nodes. And all of these end up giving very different answers, and it's not neither of them very nice and not very meaningful. And so what we ended up doing was generalize this derivation of Brownian bridges a little bit. So instead of cutting it at 5, we model it as it actually happens. So you start at 5 and you have two paths going to 3. And so I call these two paths here W1 and W2. And these are similar as before. You had some two independent Brownian motions going down these two sides, but we condition them to come back at 3, and the amount of time of this loop is capital T. So it's a little bit more general condition than saying it comes back to a specific point. But in a rough formulation, this still ends up looking something like a Brownian bridge, except that this endpoint X is no longer fixed, and that distribution is computed from this condition on the right on top. Okay, so what this does is it simplifies your problem, and you go back to this idea of shared time matrices. So if you have this tree, this arc, and this is the process you're trying to model, the covariance at the tips ends up depending on a shared time matrix, but related to the paths. Instead of looking at just the samples, you look at every possible path. So there's one path associated with 2. There are 2 paths associated with 1, and you compute the shared time between each of these paths. So instead of having 2 things that you're computing the shared time between, now there are 3 things that you are. And the covariance depends in sort of a complex way on this, but this is the object that you end up with after doing this generalization using Brownian bridges. And then you can do your usual inference using these matrices. What it allows you to do is see a simulation where we ended up where to demonstrate the usefulness. So if you have 2 populations that came together, and we pick an individual from the contemporary population that has sort of a genome, parts of the genome tracing back to these 2 different populations. Here, just focusing on a particular region, there are just regions of the genome that come from different source populations. These are our simulations, so we know that firsthand. And the wavy lines are the truth, and the inferred one is in the white, and the confidence intervals are the shaded regions. So you can see that this tracks these locations pretty decently, and that was sort of the utility of being able to do this. There's some issues with the method, and I won't go into it today, but both the method and the usefulness as well as the challenges of it are in a preprint. and I'm happy to chat more about it. Okay, I'm going to take a little bit of gear shift here and move to the second property of Brownian bridges, and that's being able to model what are known as empirical distributions. So, what do I mean by an empirical distribution? So, let's start with the proper distribution, the usual one. This is for a uniform rank variable that takes a uniform rank 1 and 4, and this is the true CDF. F of x, which is basically the probability that a random sample is less than x. As a uniform variable, so it sort of just increases linearly. So it has to start at 0, end at 1, and the joining for a uniform random variable is linear. This doesn't need to be uniform. This is just to sort of just to exemplify the property. What do I mean by an empirical CDF? Is suppose I sample 10 samples from this distribution and look at how many of these, or what proportion of these are less than x. So it's an empirical, it's the CDF for like your sample, and for 10 you will see 10 jumps. The first sample is somewhere around 1.5. There's one at around somewhere a little bit over 2, and so you have these step-like empirical CDF. And this is just plotting the difference between the two, the true and the empirical CDF. Of course, every time you sample, you get a different empirical CDF, and so you have a distribution that you show ends up, and so you have a distribution of these differences. As you might imagine, the reason for doing this is that looks like a Brownian bridge, and that is the theorem. It's known that the empirical distribution converges in probability, so it converges in distribution to the difference converges to a distribution to the Brownian bridge, and the properties depend on your true CDF. And that's sort of, and I'm happy to talk about what the intuition behind this convergence is. But what this allows you to do, and this is not an exact thing, but you can write down the empirical distribution as your true CDF plus a Brownian bridge with an appropriate 1/√10 scaling. So this is not exact, but it captures the variance covariance structure because of these finite sampling from some distribution. Okay, so here's an example for the 10. So you have the sample of 10, the true CDF, the empirical CDF, which is the actual difference. And this is what you would expect from a Brownian bridge with the right parameterization. And you see that it matches, but of course it's a bit more coarse-grained. By the time you get to 50 samples, the two match up pretty well. It's around 20-30 samples that more or less everyone, it's pretty decent, and by 50 it's almost sort of, it matches what you expect from a Brownian bridge. So what did we end up, what was the particular use case, or where we ended up using this, was we were trying to model recombination landscape. So basically x is the location along the genome, and f of x is the CDF for recombination probability. So it's the probability that you have a recombination event left of x on your genome location. And then we said that suppose there are mutations that sort of fall on your genome that modify these recombination probability by some mechanism, and the location of these mutations that modify your recombination is given by this script f of x. But in reality, you only have a finite number of mutations falling, whereas the script f of x is for like as if you have a large number of mutations. So where the actual mutations end up landing is an empirical distribution of this script f. So you start with the landscape that you of an individual. You have some finite number of mutations. Each of those mutations have some effect, or E, and where they land is modeled by the empirical distribution related to script f of x. And that's where the Brownian bridge approximation came in. And what this allowed us to do is capture the variance covariance structure along the genome for this problem. So just a quick summary of like a neat result is we can compute this through the covariance at two different locations of this recombination landscape, and that gives you something that looks like this, which matches an OU model, but a multivariate OU model. So you have a bunch of OU processes along your genome in some sense, and the covariance structure is mediated by this script f, so this distribution mutations that modified your recombination rate. So some formulation like this allows you to compute the various covariance of this recombination landscape, say along a phylogeny. So you can measure how fast these recombination landscapes are evolving. If you have the landscapes at the tip, this process allows you to model that. Some of the other applications, so one known application is what's called as the Kolmogorov-Smirnov test, where basically you're testing if a particular distribution, a particular measured value comes from a proposed distribution, and that ends up using these Brownian bridges. Other applications are, we did it for the combination landscape, but you can use it to model any kind of function value trait. The other thing is it gives good finite population. So obviously, way to work with those distributions and make some progress in some problems. There are other objects that generalize this instead of Brownian motion. You can use Levy processors. And previously, we saw one of Markov bridges come up with for inference in the C dormancy term. And so there are quite a few applications of these. And I just wanted to sort of present how we ended up using it and talk a bit more about these objects. This allows you some control. I think that's all I have for the talk. There, I talked about a couple of projects. The spatial inference was with James and UC Davis. The recombination landscape was with Matt and Nicole at QFT, and Matt is involved in both of those projects. Thank you. I'm happy to take.
We have time for questions. And Florian, can you come up while we're doing this? I have this vague recollection that Brownian motion in like 2 dimensions is a bit more tricky. So have you, in the context of the linear case, have you looked at that or like?
Yeah, so you can, so, okay, if you're modeling these, the conditioning is always a bit problem. It's like, so the probability of meeting even dimension is very low, and in 2 dimension, it's even becomes lower and lower and lower. So there are issues with it, but you can still get the conditional distribution even for a 2-dimensional case. But that is what I said is an issue, is like when you make these inferences, you have these biases track in because of conditioning on this really low probability event happening. And so there are some ways of getting, there might be some ways of getting around it, but that's the issue with, but you can still do everything I talked about with Brownian bridges. It might not be the right thing for inference in those spatial cases.
Right.
Yeah.
Thank you. Very cool talk. I was wondering similarly, how does selection will affect this picture?
Yes.
Especially, yeah.
So we were thinking of the selection part, and that's the and so this is for the recombination part, I presume. Yeah. So for that, the issue with this selection is not so much as that the distributions get fixed. Like once you have it, you have to be specific of like when recombination occurs, where they flip, and that's a bit complicated. So we haven't quite figured that out yet. So we just got these situations, and we have some ideas of how you can do that, but it's a bit heuristic at the moment. Yeah.
Hi. So when you're calculating your shared time matrix, do you like just include the minimal paths that a code can get through within the loop to avoid the dependent dispersal, or do you like assume that the cells in your matrix can be dependent with each other?
They can be. They can be dependent. So you allow them to go through any path. So you need to take every path that's possible through these networks, and you can reduce how many of them you use in some systematic way. But it is equivalent to saying you take all paths through all possible ways, and if the shared time matrix is the object that is important for computing the covariance of the samples. Does that answer you?
Great. All right. Let's thank Puneeth again.